Hi, Lester, Wushu engineer. Well, this video is actually a bit of a follow-on from one of my previous videos on brick breaking, and there was a bit of an odd result that occurred during one of my brick breaking attempts, in which I failed to break the brick, and then afterwards broke it, and the values on the load cell were different. Now I had a fairly clear idea of what was actually going on there, but when we're talking about measurements associated with human movement, there are usually a lot of variables that are at play, and in this particular case there were at least two. Well, actually not just two, there were actually many variables at play, but some of the variables that were at play were things like my acceleration, in other words the acceleration of my arm, so the final velocity at which my hand was moving, the structural integrity of each brick, as well as the apparent mass behind my strike. So there were several variables that were at play there, and it made making a generalized observation about what was occurring very difficult. So I went on to do a series of further tests using, in this case what I used was a 5 kilogram mass, a rubberized dumbbell, dropped from various heights to eliminate some of those variables, at least some of them. So the variables that I could eliminate by doing that were the velocity, because an object dropped from a particular height is going to achieve a particular velocity in accordance with kinematic equations. And I could also eliminate the apparent mass that was at play, because of course the mass there would be limited to 5 kilograms. And so I did a series of tests. I first did a series of tests doing brick breaking manually with my hand, and we'll have a look at those tests first, and then we'll have a look at a few clips from the tests with the 5 kilogram dumbbells. And you'll note that I did a series of tests where I was actually doing brick breaking with the dumbbells, and and then I also dropped the dumbbell from those particular heights without any bricks in place. So just measuring on the load cell what the peak forces were at the impact. And then I repeated those tests using the PowerKube device as well, so that there was a little bit of a cross-reference there for those of you who actually have the PowerKube 3 device and who are using it. You can cross-reference that. So these are tests done dropping 5 kilogram weight from 1.5 meters above the surface, from 1 meter above the surface, from 500 above the surface, from 400 above the surface, 300 and 250. So those were the set of standard heights that I was using. I didn't have a lot of time, so I didn't repeat the test as many times as I should have. I should have at least gotten a sample size of maybe 10 to 15 tests, but that would have taken a long time. So I kept the number of tests down to a minimum of 3 for the PowerKube, and I just did a single test at each height on the load cell without any bricks in play. So I'll run some of those clips. I'm not going to play all of the test footage, because in the first place it's pretty boring, and in the second place it would just take too long. There's a lot of footage, so I'll play little clips from each of the test procedures so you could see what I was doing, what I was getting up to. So I'll first run the clips of my actual manual brick breaks along with some of the attendant values, and then we'll go into the tests with the 5 kilogram dumbbell. And after that, I'll get you back here and I'll show you some of the graphs that we got from the load cell, also some of the values from the PowerKube, and we'll have a little bit of a chat about what is actually happening. Well, what I believe is actually happening in terms of the mechanics, and from that you can actually draw some fairly good conclusions about how to achieve good brick breaking technique. So this is not necessarily a how-to video, but it is a let's say my take on a scientific analysis of the process of manual brick breaking. So I'll run some of those test clips, and then we'll get back to the results and conclusion section. See you then. So what I've got set up here is a standard as just a plywood sheet on top of the load cell, just to protect the aluminium plate of the load cell from getting damaged by the brick breaking. I've got a pair of bricks as the supports on the side, and then I've got a narrow hard-fired clay paver resting on the top, with of course a telephone directory to save my hands. It's been a while since I've actually broken these types of bricks, so it might be a little bit of an overkill or an underkill. And we'll establish what force is required to break these, and then we will look at how not to break the brick, but still putting in the same amount of force, whether it's possible for me to do that. Start off zero the software, start the recording, and see what happens. Okay, stop that. So I'll redo that. There was just a little bit of a problem with the software. It didn't, the maximum didn't come through, but it was just over 1,500 newtons. Of course, we'll have a look at that in more detail when we discuss the when we go into the results section. But I'll just break one more just to kind of ensure that we've got the breaking force. Okay, so that was not a break. That went up to 2,000 newtons. And that was a break, and that was well under 2,000 newtons. So I've actually already done what I was intending to do, and that was in the same experiment. So I'll zero that again. We'll see if we can't recreate that event again. So I'm going to try and hit hard without breaking it. Okay, I'm going to try and hit hard again without breaking it. Yeah, it just slipped off. Just put it back on again. Try again. And again. That just slipped off again. And those strikes were all up around the 2,000 Newton range. So now I'm going to break it. And you'll not believe how much force was required to break it. It was under 1,000 newtons. Just for fun, while I'm doing this, let's try a stack of them, eh? A stack of 3. See if I can selectively break the brick at the bottom. Zero that. Telephone directory. And we'll start. Right. There we go. And what is interesting again is that the first 2 strikes were over 2,000 newtons, and the strike that broke the bottom brick was about just under 1,500 newtons again. Just see if we can break these other two. There we go. So, the amount of force to break 2 stacked bricks was also just around 1,500 newtons. Almost the same as to break 1. So what exactly is happening? Okay, so once again, excuse the shorts, it's Queensland, it's summer. So what I'm going to do here is I'm going to be dropping a 5 kilogram object, a dumbbell, from which is actually rubberized, from various heights. It's not exactly the same as my hand, but the pattern pretty much fits the profile, the area of my palm that strikes the brick when I'm doing the brick breaks manually with my hand. So we'll see what happens.
Okay, so I'm going to press start.
I'm going to be dropping from 1.5 meters above the surface, at least initially. Okay, tell me when to go.
Okay, you can go. Okay, so that was 1919.
Okay, so just stop that there. We'll do that a few more times. So I'm going to redo some of those tests from various heights with the 5 kilogram weight on the load cell, and we'll see what those results look like. Start off off. Okay, so I'm going to do some of the 5 kilogram drops from various heights, measuring the results on the PowerKube. Unfortunately, you're probably not going to be able to see the screen from that camera angle, but unfortunately it's necessary to get everything into the shot. But I'll be calling them out and I'll be recording them as well as we go along through the tests. Okay, so I'll just get started here. That's 1.5 meters, is 12,932. Okay, so we're back to the results and conclusion section. So these are some of the graphs that I've plotted based on the values that we got from the load cell. Now I'm hoping that you're going to be able to see these, because it would just take too long to try and draw these out on the whiteboard. But you'll notice, I hope you'll notice, a series of numbers at the bottom. Those are all, essentially those are time divisions, and each one of those numbers represents 1 millisecond. So so there's actually quite a lot of data that's being, what I should say is that the time scale here is actually quite small. So we're actually looking at events that are occurring in the millisecond range. This is a series of graphs from my brick breaking attempts. You'll notice that some of these graphs are quite low, and generally speaking, the lower graphs, so in other words, the graphs that are cut off prematurely, are actually plots of the brick break. So what is actually occurring is that when the brick is broken, the structure is essentially compromised and can no longer effectively transmit force into the load cell. So at the point where the brick breaks, the peak essentially starts turning, and that's why when you break the brick, the force that the load cell sees is lower than if you didn't break the brick, because obviously with an unbroken brick, a lot of the force from your, well, all of the force from your strike can actually effectively be transmitted through that structure into the load cell below. Whereas if you break the brick can no longer transmit that force into the load cell below, and so the peak is locked. Another interesting thing to note about the peaks is that you'll notice that the gradient, essentially the gradient of each one of these peaks, which of course is the point at which the brick is either breaking or not breaking, are actually all fairly similar for my manual brick breaks. So that's something to note for future reference when we have a look at another series of graphs. So really quite interesting to see that the waveform is actually very similar in all cases. You'll notice as well here at some of these breaks there's a peak which is lopped, it drops down, and then there's a secondary peak which occurs over here, so it doesn't actually dip as far below the other graphs as the graphs of the unbroken bricks. And what is actually occurring there is that the brick is breaking, and the pieces of the brick are actually moving down. You can imagine it in slow motion, moving down and finally impacting the bottom of the plate, in other words the top of the load cell. So this is the point at which the brick is breaking for this blue graph. It's dropping down, the pieces of brick are dropping down and then finally hitting the bottom, and that's when some more force from my blow is being transmitted into the load cell below. So quite interesting to see these events at such small time scales. So I'm going to have a look now at a series of tests done with the 5 kilogram weight dropped from various heights. Exactly the same phenomenon was present there, in which in that when the brick was broken, the peak was locked, and then the rest of the structure, in many of the cases early on, but in some cases a little bit further on, the rest of the structure from the broken brick hit the load cell and then transmitted force into the load cell again, giving a secondary peak. And what is interesting is that in some of them that secondary peak was actually higher than the peak that broke the brick in the first place. These two high peaks over here, the blue and the yellow, are actually tests run at 250 and 300 above the surface of the brick, and those were fails. So the brick did not break, which allowed all of the force of that impact to be transmitted into the load cell below. So once again, really interesting. Same phenomenon over there. Same phenomenon present in that in the tests without my intervention. So they're just dropping weights from various heights. I also did a series of tests on the load cell without any bricks in play. So this was just with a telephone directory on the top of the load cell and dropping the brick from those same set heights, and we'll see what we would have expected to see, which is a very high peak from for the drop at 1.5 meters, a slightly lower peak for the drop at 1 meter, and then 500, 400, 300, and 250. So very much what we would expect to see. But the really interesting thing to note here is that the gradient of each of these peaks is clearly changing. So as the height increases, the peak, the gradient of that first part of the peak is increasing significantly enough to actually be seen on this graph. And that's really interesting, because I believe that is more a function of the velocity of that, the final velocity of that 5 kilogram weight. So I'm going to draw your attention back to my set of brick breaks again, and you'll note there that, as I mentioned before, the gradient of the first part of these peaks is all fairly similar. And what I believe is happening is that the velocity that I'm achieving with my hand is pretty consistent across each of those brick breaks. So what exactly is actually, well, first, actually before I get onto that, we'll have a quick look at the values on the PowerKube as well. So I've plotted out a histogram of the PowerKube values, and I've calculated some averages. So at 1.5 meters, the PowerKube registers 12,000 Franklins. At 1 meter above the surface, it measures as around 7,300 Franklins, and then just over 3,000 for half a meter, 2,300 for 0.4 meters, 1,669 at 0.3 meters, and 1,191 at 0.25 meters. So you'll see how the graph goes, and this is pretty much what we would expect, and it's fairly consistent with the results that we achieved on the load cell, except obviously with different units at play. So for those of you who are interested, this is now cross-referenced. This is the same test cross-referenced and done on the PowerKube. So what exactly is happening? Why are the bricks breaking at specific points and not at others? Well, I believe that ultimately what is breaking the bricks is kinetic energy, ultimately. So kinetic energy is generally required to break structural and molecular bonds, and that's precisely what's happening in the brick. When the brick is broken, bonds are being broken, the brick shatters and breaks, energy is absorbed, energy is required to do that. So we're not necessarily looking at the kind of force that's required to break a brick. As a matter of interest, I did do a little bit of research and found an old paper published in the UK which gave some values for the amount of shear force required to snap a brick in half, and the kind of bricks that I was using, it suggests this is not extremely accurate. This is just an extrapolation based on their study, so I'm not using the same bricks that they were using. So this is just really like a very basic idea of what kind of shear force is required to break that brick. Is probably somewhere in the region of 800 to 1,000 kilograms. So around nearly a ton of force required to shear that brick. So for me to stand there and try and push down on the brick to break it without creating some kind of impact would pretty much be impossible, because I'd have to press down with a ton of force with one hand to break that brick in half. So what is occurring is an energy-based break. I'm providing enough energy, and of course the equation for kinetic energy, as we all know, is half mass times velocity squared. So both mass and velocity have a part to play in that equation. Velocity plays more of a role, obviously, because it's squared. Mass plays less of a role. But when we're talking about human movement, there are very definite limitations to how fast a human being can move because of the way that our muscles work. Our muscles contract at particular speeds. And while we can always improve on that, there's certainly very, very, very strong limitations on how fast we can actually move. So velocity is always going to be something that we'd like to improve, but it's very difficult to do so past a certain limit. Whereas if we look at the mass part of the kinetic energy equation, mass is something that's a little bit easier for us to manipulate, because we can potentially, while we are doing the movement, we can draw on our own body mass and also our structural connection to the ground and to various other surfaces to improve or to increase the amount of mass that is apparent behind our strike. So what I'm doing when I'm breaking that brick is I am trying to achieve maximum velocity, but at the point of impact I am trying to modify how much mass, apparent mass, the brick sees behind my hand. So my arm would weigh somewhere in the region of 5 kilograms in total, but of course because it's a long lever, it's not just 5 kilograms of mass in my hand. But if I reference my body weight, my body mass, I can increase that to to a certain value, which is higher than what it would be if I was just dropping my arm on the brick. So essentially that's what I believe is occurring during a brick break, and that's why timing is so critical, because if you try and apply that apparent mass prematurely, it can tend to slow your movement down because your muscles start engaging prematurely, and then your velocity drops off, which means that the attendant mass that you have, the apparent mass you have to produce, becomes much higher, because of course, remember, in the kinetic energy equation, velocity is squared. So we really want to try and keep that velocity very high. But at the point of impact, so not before or after, we have to time this to occur at exactly the point when we make contact with the brick. We want to increase our apparent mass so that we can then bridge the gap and inject enough kinetic energy into that brick to cause it to break. So that is what I believe is happening. The bricks are breaking due to kinetic energy, and the kinetic energy that I am producing is a combination of my maximum velocity that I can achieve and my apparent mass, so the way that I modify the mass of my arm through muscular control and connection through to my center of mass to increase that kinetic energy to the point where the brick breaks. Alright, well I hope you enjoyed that. There was actually quite a lot of work that went into this video, and it took a little bit longer to produce, and it's probably going to be a bit longer in length. I hope you enjoyed that. If you want to see more of this kind of thing, let me know, and leave a comment in the comment section below if you liked it, and let me know if you have any other ideas that you'd like to see me investigate. I've got a long list and I'm slowly getting to them, but do leave suggestions. I do listen to them all. Alright, see you next time. Cheers.